right, let's take a look here today at spherical coordinates. It's just another way of representing points and equations. Of course, obvious reasons. It's good for spheres, cones, things like that. But just a little bit about the coordinate system first. If we have a point here in 3 dimensions, spherical coordinates are determined this way. So we've got this point somewhere out here in space. That point x, y, z is equal to, in spherical coordinates, rho, theta, and phi, or phi, as determined by this. Rho is just the distance from the origin to that point. Rho is the distance from the origin to our point, straight to it there. And for obvious reasons, rho has to be greater than or equal to 0. Theta is one we're familiar with. Theta is the same angle theta as in polar or cylindrical coordinates. And that is, it's the angle made here in the xy plane from the positive x-axis. And so let's say this point drops down to here in the xy axis. And so theta is that angle right there. Okay. So it's basically between theta and that line in the xy plane. Okay. Phi, on the other hand, this is rho, and this is phi. Phi is the angle here that we make with the positive z-axis. That's the angle. So it's here's our line to the point, and so phi is the angle we measure from the positive z-axis to that line. So it's angle between the positive z-axis and the line from the origin to the point. And there is a restriction on phi. It has to be the maximum it can be is 180 pi degrees. So it ranges from 0 to pi. Theta can be any angle, but the restrictions on phi is that it has to be from 0 to pi, and sometimes you might see this phi as might look more like that. It's just a little bit of difference in the upper and the lowercase Greek letter there. Okay. All right. Now we might notice a couple of things here. First of all, that this is what we've been calling r, this distance from the origin out to the point in the xy plane that's associated with that point. And then, of course, this is the height z of our point. And so based on the angle phi, because that angle phi would be the same angle would be in this right triangle here that we've got, RZ and then rho. We might notice then that Z would equal rho times the cosine of phi. And then R would equal, down here, R would equal rho times sine of phi. Just from the trig function relationships there. Okay. Well, what that sets up then is if we're given the spherical coordinates rho, theta, phi, then the cylindrical coordinates that would match up with that, which in cylindrical we do R and then theta and then Z. Well, like we said, R would be rho sine phi. Of course, theta would be equal to theta. That's the same angle. And then Z would equal rho cosine phi. So we could convert, just see the relationship. Okay? Now we also might note here, again from the triangle, that we've got a little Pythagorean theorem going on here. So we've got R squared plus Z squared would equal rho squared. Okay. And then knowing what we know about, let's go ahead and talk about then going from spherical to Cartesian, or vice versa. Right there. From cylindrical and polar, we know that x equals r cosine of theta. Well, if r in this case is, just wrote it down, r was rho sine phi, then if we make that substitution there, we have rho sine phi cosine theta. That would equal the x. And so that would give us a way to convert from spherical to the x value. And then the y value, of course, is r. We know that's r sine theta. And so r again is rho sine phi. So y would be rho sine phi times sine of theta. That would give us our y. And then, of course, z in Cartesian, we already know that's rho cosine phi. Okay? And one other quick point here. Again, we know that rho squared equals r squared plus z squared. And then from the fact that we know from polar or cylindrical, r squared equals x squared plus y squared. And so if we make that, we get a nice conversion for rho there. rho squared equals the square root of x squared plus y squared plus z squared. So those all should help us along the way if we need to convert from one to the other. That, of course, helps us if we have Cartesian. This will help us find the rho value for our angle, and then we can find the other angles accordingly. But let's just talk about let's take one that's in spherical here and plot it and convert it to Cartesian. So let's plot the point with spherical coordinates. Two square root of 2, comma, pi over 4, comma, pi over 3. Plot it and then convert it to Cartesian. Okay, so yeah, what we know here, all right, so this is our rho, this is our theta, and this is our phi. So rho is 2 square root of 2, theta is pi over 4, and phi equals pi over 3. Well, starting with what we know, theta is pi over 4. That's the angle in the xy plane from the positive x-axis. And so we know we're going to go out 45 degrees here. So it's somewhere along that, with that. Okay. Now, we're going to rotate, phi is the angle from the z-axis, positive z-axis, and so we're going to rotate along this line, and we're going to rotate it pi over 3, 60 degrees. So we're going to come out here and rotate pi over 3, this is pi over 4 degrees, and it's got to be kind of in this plane here, so pi over 3, and the rho tells us how far from the origin we're going to go out from that, and so 2 square root of 2 units out there, and so we're somewhere out, sitting out in space right about here. Now okay, and so this line comes down something like that. So we're out from this coming out of the board there, but kind of hard to sometimes draw, but that's what we got. Okay. All right. Now in Cartesian, we know x equals r cosine theta, and r is rho sine phi. And so x is going to be rho, which is 2 square root of 2, times sine of phi, sine of pi over 3, which is square root of 3 over 2. And cosine of theta, which is pi over 4, so that would be square root of 2 over 2. And so we wind up with, 2's cancel, so we wind up with 2 square root of 3 over 2, so that's just square root of 3. The x value is square root of 3. The y then would be r sine theta, but r in spherical is rho sine phi. So we have rho sine phi times sine of theta. So y would be 2 square root of 2 times sine of pi over 3, which is square root of 3 over 2. And then sine of pi over 4 is also square root of 2 over 2, so that's going to work out to be also square root of 3, same numbers. Turns out in that case. All right, and then z equals rho cosine phi, and so that would be 2 square root of 2 times the cosine of pi over 3. how you get your z. So that would be 2 square root of 2. Cosine of pi over 3 would be a half. And so we're talking about z being the square root of 2. So it's square root of 3, comma, square root of 3, comma, square root of 2. Okay? All right. Now, if we go the other way, let's do one just to see what we're talking about there. What we run into there. Okay, so let's convert -1, 1, negative square root of 2 from Cartesian to spherical. Go the other way here. Okay, so we want a rho, theta, and phi. Okay, so rho said if we know that rho squared equals x squared plus y squared plus z squared, then obviously rho, since it's greater than or equal to 0, is the square root of x squared plus y squared plus z squared. So rho is going to be the square root of -1 squared 1, +1 squared 1, and then -2, a negative square root of 2 squared, that would be 2. So rho is going to be the square root of 4, which is +2. Okay? All right. Now, we know, thetas are regular theta, and we know that the tangent of theta equals y over x, and so here theta would be, tangent of theta would equal 1 over -1, and so that is tangent of theta equals -1, which if we do our inverse tangent, well, the inverse tangent here actually gives us pi over 4. However, if you think about in the xy plane here, we're talking about -1, +1, and so just looking at the xy part of this, we've got x is -1 and y is +1. So we're talking about quadrant 2 in the xy plane here. Here's our our theta then is this. And so that's not going to be pi over 4. That's going to be our second quadrant angle where we have a reference angle of pi over 4. So that'd be theta would be 3 pi over 4. Quadrant 2. As far as the xy plane. Okay? Then for phi, well, we know that we can get that pretty easily from z equals our conversion there. Z equals rho cosine phi. And so the cosine of phi is equal to z over rho, which we do know. So the cosine of theta is negative square root of 2 over 2. We know z is given the square root of 2, negative square root of 2, and rho is +2. And so there, if we do our inverse cosine, because of the restrictions on theta, we can definitely get that. That, of course, is 3 pi over 4 also. Oh, sorry. These are phi's, not thetas. So the cosine of phi is z over rho. So the cosine of phi would be negative square root of 2. So phi is going to be the inverse cosine of square root of 2 over 2. So phi is also 3 pi over 4. So in spherical, this would be rho, which is 2, theta, which is 3 pi over 4, phi, which is 3 pi over 4 as well. Okay, so you just run into some angle things you have to interpret sometimes. All right. Let's think about some surfaces here. That are given in spherical coordinates. If we have rho equals 5, well, this is one of the good things about having spherical coordinates. Rho equals 5, if you think about it, means we square both sides. We have rho squared equals 25. And rho squared equals x squared plus y squared plus z squared. The equation rho equals 5 is synonymous with x squared plus y squared plus z squared equals 25, which we know happens to be a sphere of radius 5, centered at the origin. Okay, so rho equals 5 is a nice, neat equation for describing a sphere. Rho equals any constant would be a sphere centered at the origin at that radius. All right. Also, like we said before, spherical coordinates are good for spheres. And they're also good here for this one. This is phi equals pi over 3. So that means we're talking about all the points with the angle phi equals pi over 3. Well, that's the angle with the z-axis. And so we're talking about all of these points where we have an angle of pi over 3 from the z-axis. All right, and so if you think about all those points where we've got that angle being pi over 3, so if we go around here, with all those angles, same pi over 3, so rotate out that way, and then this way, and so we get what we wind up getting is a cone, because yeah, you can just keep those going. It doesn't have to be necessarily that long. And so you just get a nice cone shape, infilly going infilly out there. So yeah, phi equals pi over 3, that's the cone above the xy plane. With the angle being pi over 3. If we change that to pi over 4, then it's going to be slightly narrower, I guess, or make it bigger than pi over 3. Yeah, so you can make your cone as wide or as narrow as you want. Now, how would we get it? Let me ask you this: how would we get a cone that's below the xy plane in this orientation of our coordinate system anyway? Well, if we want a cone below the xy plane, then you think about it, I need this angle here. I need this angle here to be where then our go further there. So we've got to go past the xy plane to make it below, like here. So yeah, we're going to have to, how would we get one like that? Well, to go past the xy plane would be at pi over 2, and so we're going to have to go beyond pi over 2. So phi equals c, where c is somewhere between pi over 2 and pi. That's how you could put this. Sorry. That's how you get. So you're going to go to the xy plane and then just go beyond it. And so phi equals something between pi over 2 and pi would give you a cone below the xy plane, upside down in our normal orientation there. Okay. All right, so let's also here a couple other things with spherical. So yeah, cones and spheres, very good to write in spherical coordinates. Easy to write. All right, so just real quick, convert to spherical these equations. X squared plus y squared equals 4. Well, first of all, we might, instead of going to spherical here, we might change it to a simpler form that we know. We know that x squared plus y squared equals r squared, so this is r squared equals 4. And since r has to be also greater than 0, we would know that r here would equal 2. And we know from our original drawing there that r, because of the right triangle that we get in spherical coordinates, where this is our kind of our angled this is r, and this is phi, so r is equal to rho sine of phi that gives us a little conversion there. So change this to r squared, which we can square root to get to r, and r is rho sine phi because of the right triangle we know these make. So yeah, there you go. In spherical terms, x squared plus y squared equals 4. Now, what do we know about x squared plus y squared equals 4? Well, x squared plus y squared in the xy plane is just a circle, and so if we extend that to 3 dimensions, that's a cylinder. So it's a cylinder radius 4, and so one other way you could look at it is this in spherical coordinates is a cylinder of radius 2. Probably not quite as easy to recognize, but that's what it is in spherical, cylinder of radius 2. Okay. What about x squared plus y squared plus z squared plus 2z equals 0? What would that look like in spherical coordinates? Well, again, you're looking for these things. X squared plus y squared plus z squared, we know that's rho squared, which is spherical. And then the only other thing we need to convert is the z. Well, we know z is rho cosine phi. So this is actually maybe an easier one than the first one. So spherical coordinates, that would be the equation of that, which that's going to be a sphere shifted shifted a little bit. I guess 2 units down, but or square root of 2 units down. But anyway, yeah, okay. All right. Well, talk about integration here. Let's talk about integrating with spherical coordinates. Well, it turns out if we're integrating over region E, the function f of x, y, z, dv, turns out dv is, in cylindrical coordinates, dv is r, dr, d theta. Well, in spherical coordinates, dv equals, the book shows y, but it's rho squared sine of phi d rho d theta d phi. So that's the conversion there in spherical. The good thing is, rho is just going to range from, a fixed amount, A to B, they usually call it. So how far out you go from your origin there. And of course, d theta, we usually rotate it from alpha to beta, how much it changes in the xy plane, the angle there. And then phi, well, it's also going to range between two angles. And I believe this book calls it C to D. Gamma to delta, I think, in some places. So this integral then, triple integral over region E, fxyz dv. In spherical coordinates, that's the usual order there, so there we go. So phi is C to D, theta is alpha to beta, and rho is from A to B. Now, because of the conversions, we know x is r cosine theta, so that would be rho sine phi cosine theta. Y is r sine theta, so it would be rho sine phi sine of theta. And then z is rho cosine phi. So based on those conversions, convert your f to whatever function that is. And then you have times rho squared sine of phi. Just like in spherical, we add the r with our dr and d theta and all that. D rho, d theta, d phi. That's the order we try to do those. Okay? All right. So it looks pretty bad, but usually it's not too bad. So let's do one here for this. We evaluate the triple integral over region E, 16z dv, where E is the upper half of the sphere, x squared plus y squared equals z squared. X squared plus y squared plus z squared equals 1, I should say. Okay. So we've got the upper half of that sphere is what region E is here, and we're going to integrate 16z with respect to it. So, yeah, the hard part here basically is getting our limits for rho and theta and phi. Well, since we're talking about a sphere, you know, x squared plus y squared plus z squared equals 1, that is simply then rho equals 1, isn't it? And so we're integrating over that solid top half of the sphere, and so rho here is going to range from 0 to 1 to the outside of the sphere. Okay, so that one's easy enough, since that's what that is. That's a sphere of radius 1. So rho will go from 0 out to 1. All right, and if you think about it in the xy plane, then we're talking about top half of the sphere, and so theta's going to go all the way around. Theta goes from 0 to 2 pi. And since we're only talking about in the top half here, so we're talking about this doing the top half of the sphere. Yeah, the angles phi here, well, the maximum angle I'm going to get, I'm only going to go to the xy plane, and so that would give my phi the range of 0 to pi over 2, because I'm going from this tip, and then the maximum angle I would get out of that would be down to the xy plane, which would be pi over 2. Nothing below the xy plane. Okay? All right, so that makes our triple integral here. Then what? Well, phi is going from 0 to pi over 2. Theta is going from 0 to 2 pi. And then rho is from 0 to 1. Our function is 16z. Well, we know z is rho cosine phi. And then dv, the conversion is rho squared sine of phi. So we have rho squared sine of phi. And then it's d rho d theta d phi. Okay? All right. So we're integrating rho first, so that would be phi cubed. So that integral, 0 to pi over 2, 0 to 2 pi. The first integral, we got 16 times, will be 1/4 rho to the 4th, right? Because that's rho cubed, so antiderivative is 1/4 rho to the 4th. Times, we got cosine phi sine phi. And that's going from 0 to 1 for rho, d theta phi. All right, so we plug in the 1 for rho, you got 1. All right, so it's, and that of course reduces to 4. So we got 0 to pi over 2, 0 to 2 pi, and we just have 4. Now, this is cosine, done that a couple of times. Just make that 1/2 sine of 2 phi, if you want to, which helps us out with the 4 there. And yeah, we're left with 2 there. And you might notice here we don't have any thetas, so we could just separate that out. Couldn't we? 0 to pi over 2 sine be 2 sine of phi d phi times the integral 0 to 2 pi what's d phi, and do this one d theta, just 1 d theta. Right here yet. So it's 2 sine of 2 phi d phi times just the integral. That's just going to be 2 pi, isn't it? We're just doing 1 d theta. 0 to pi over 2, so this would be u is 2 phi, so that'd be a half, so we're just going to have sine of, negative sine of u, so the antiderivative is negative cosine of u, so it'd be negative, the 2's are going to cancel because you have a factor of a half. Anyway, so we're going to do negative cosine of 2 phi from 0 to pi over 2, which makes it, let's see, pi over 2, the cosine of pi over 2, that's 0, minus cosine of 0 is negative 1. Oh, sorry. That's not correct. Okay. All right, so if we plug in pi over 2, we have the cosine of negative the cosine of pi minus negative cosine of 0. So it's plus cosine of 0. Cosine of pi is negative 1, so negative cosine of... Do it over here. Okay. So this would be... cosine of pi is negative 1, so negative cosine of pi would be positive 1, plus positive 1, so we have 2 times 2 pi, which is 4 pi. Okay. All right. Okay, all right, let's see. Do one more here. Triple integral, spherical. Actually, for this one, I'm just going to convert. Let's convert integral 0 to 3. 0 to the square root of 9 minus y squared, square root of x squared plus y squared, to the square root of 18 minus x squared minus y squared, x squared plus y squared plus z squared, dz, dx, dy. Convert that into spherical coordinates. Okay, so what we've got, of course, z here is between these two. So square root of x squared plus y squared to the 18 minus x squared minus y squared. The next is the x, so x is between 0 and the square root of 9 minus y squared. And then y, of course, 0 to 3. All right. So let's look at these two first. This tells me, if you're just looking at in the xy plane here, we're going square root of 9 minus y squared is that. It's the right half of a circle. And since y is only ranging from 0 to 3, we're talking about a quarter circle there. And so what that gives me is the fact that theta here, since theta is the angle in the xy plane, theta has to be between 0 and pi over 2. Okay? All right, now, if we look at the z here, the lower bound of z, we've got the square root of x squared plus y squared. Well, that tells me we're talking about a cone, top half of a cone. Recognize that. And then the upper bound, z equals the square root of 18 minus x squared minus y squared. What about that? Well, if you square both sides, you got z squared equals 18 minus x squared minus y squared, which is x squared plus y squared plus z squared equals 18. And so there we're talking about a sphere, radius square root of 18, centered at the origin. And since we're doing the square root of it, that's the top half of the sphere. And so basically what we're doing, we're integrating over, well, it's the top half of a cone to the top half of a sphere. And so one thing that tells me is my range for my row. Okay, and so I'm going out to that square root of 18, so that's the top half here. And so row is going from, my cone is in here, and so I'm going to start at 0 and then go out to the sphere there, which is, so that would tell me row is between 0 and square root of 18, or square root of 3 times the square root of 2. All right. So that leaves us my phi. Okay. Well, basically what I've got here is I need to, for phi, I need to know what where the two of these intersect, where the sphere and the cone intersect. So let's solve this equation here. Well, so my phi is where the cone and the sphere intersect. So I've got the cone, you got z equals the square root of x squared plus y squared. And for the sphere, I've got the other version of it, x squared plus y squared plus z squared equals 18. And so here, one thing I could say is that x squared plus y squared equals z squared. And so let's plug that in for x squared plus y squared. Then I'll have basically these two equals z squared. So I've got 2z squared equals 18. So z squared equals 9. So z equals 3. Well, what that helps me with is then the fact that I know that z is rho times the cosine of phi. And I know that phi is square root of 18. Then the cosine of phi would have to be equal to 3 divided by the square root of 18, which is 3 divided by 3 square root of 2, like we said. So that's 1 over the square root of 2. And so phi here, where they intersect, would be the inverse cosine of 1 over square root of 2, which is square root of 2 over 2, which is actually pi over 4. And so phi is going to range from here to pi over 4. Okay, so rho was between 0 and square root of 18 or 3 square root of 2. And then theta was 0 to pi over 2. So this integral, erase everything I'm doing here. So this integral then would be, I'd go, see we do rho first, so it'd be 0, phi first, so 0, right in our integrals, 0 to pi over 4. Then we'd have theta from 0 to pi over 2. And then rho is from 0 to 3 squared root of 2. X squared plus y squared plus z squared. Well, that's rho squared. And then dz, that's dv. So dv is rho squared sine phi d rho d theta d phi. And then, of course, those two make rho to the 4th, but basically it. Okay. All right.